In this video, we work a problem using partial fraction decomposition where the denominator has irreducible quadratic factors only. And this is an example that has irreducible quadratic factors only. We know x squared plus 4 is an irreducible quadratic because it's a sum of squares and it's been squared. At this point, I might try u substitution. I might be tempted to because I've got all of that squared. And if it works, that's the way to go. You definitely want to do that if it works. But if I take the derivative of this, I get a 2x, and that can handle the negative 3x. I'd be fine if that was the only thing up there. But I don't just have a constant times x up here. I've got an extra constant by itself. I've got a 2x squared. So u sub isn't going to work for this, and of course our basic rules don't work for this. Okay, so we're going to use partial fraction decomposition. Notice also that if I wrote x squared plus 4 times itself and I multiplied it out, I'd have an x to the 4th up front as our first term, and x to the 4th, or that we're going to have a 4th degree polynomial in the denominator. The degree of the denominator is greater than the degree of the numerator. So we're ready to go straight for PFD. So normally we'd factor first, but we don't have to on this one. It's been factored for us, which is always nice. And I want to write this as its partial fraction decomposition. That's an irreducible quadratic factor squared. So what I get is two terms, because it's squared, one with the irreducible quadratic in the denominator, and another with the irreducible quadratic squared. Now in the numerator, whenever we have irreducible quadratics here, you're going to have a constant times x plus a constant, and a constant times x plus a constant. If this is an irreducible quadratic, it needs to be linear in form in the numerator. So that's the form of our PFD. It's the first thing we do is we write that down. After we have factored the denominator completely, checked for u sub, checked for basic rules, made sure the degree of the numerator is less than the degree of the denominator. After all that, we do this. Okay. Then we multiply by the LCD, and the LCD is always the original denominator. Multiply every term by the LCD. I like to add the parentheses here just to remind myself that whole binomial is multiplied by this. The same is true over here. Okay. Now this is reducing with this. This will reduce with one of these, and this reduces with both of those. So we multiply by the LCD and then reduce or simplify. And now we're here. If I distribute here, first times first is ax cubed, outer times outer is 4ax, inner times inner is bx squared, and last times last is 4b. So we multiply with the LCD, simplify. Then we distribute and collect like terms in x. This is going to lead to a system of equations that will allow us to solve for a, b, c, and d. So I want to collect like terms in x here. This is a cubic polynomial. It has an x cubed in it. So I'm going to write my cubic term first. And then I want to write my squared term. So I've taken care of that one. And then I've got a bx squared. And then I want to take care of my x terms. I've got a 4ax and a cx. So that's 4a plus c times x. And then I want my constant terms to be over here. So that's 4b plus d. And all of that is equal to this. Now, this looks like a third degree polynomial. This looks like a second degree polynomial. It doesn't have an x cubed in it. That's okay. We just need to add a placeholder. If there are any missing terms on this side, just add 0 times that term, 0 times that power of x that's missing, so that you have the same number of terms on this side and this side. Okay, now we're going to use the fact that we talked about in the last video. The only way that the polynomial on this side is equal to the polynomial on this side is if the coefficient of x cubed on this side equals the coefficient of x cubed on this side, and the coefficient of x squared on this side equals the coefficient of x squared on this side, and so on. So 0 has to be equal to a. Well, that's nice. It gives us the value of a immediately. A is 0. And the coefficient of x squared on this side has to equal the coefficient of x squared on that side, so b must be 2. And the coefficient of x on this side, 4a plus c, has to equal the coefficient of x on that side. So 4a plus c must be -3. And then the constant term on this side has to equal the constant term on that side. So 4b plus d must be 8. Well, this is very nice. We have 4 equations and 4 unknowns, but 2 of those equations already tell us what a and b are. If I know that a is 0, this tells me that c equals -3. So now I've got a, b, and c. And if I know that b is 2, this is 8 plus d equals 8, so d must be 0. So I've got a, I've got b, I've got c, and I've got d. So we distributed, collected like terms in x. You write down a system of equations, and this time we had 4 unknowns, a, b, c, and d. You've got 4 equations and 4 unknowns by setting the coefficients of the appropriate power of x on this side equal to the coefficient of the appropriate power of x on this side. Coefficient of x cubed has to be the coefficient of x cubed. Coefficient of x squared has to be the coefficient of x squared, and so on. So you write down that system of equations, and then you solve the system. This is a really easy system. We're able to find a, b, c, and d pretty easily. Okay, now that we've got a, b, c, and d, we're going to back substitute those into the form of the partial fraction decomposition and then anti-differentiate. So our original integral is equal to ax plus b over x squared plus 4 plus cx plus d over x squared plus 4 quantity squared, and it turned out that a was 0 and b was 2, so we're going to substitute those in, and c was -3 and d was 0. So you substitute those guys in and simplify. And of course, the last thing we do in this class is we anti-differentiate. Now, in differential equations, you'll use partial fraction decomposition as well. But when you do that there, you're really not interested in anti-differentiating, most of the time anyway. When you use this in differential equations, you're just trying to write this in this other form, and then you're going to use the table of Laplace transforms to take the inverse transform. And in this class, we're using it to anti-differentiate. Claim is, after I've done this, I've got rules for each of these guys, do I? Yeah, that's fine. That's a constant over a squared plus x squared. That's an arctan. And what about this one? That's going to be a u sub. if u is x squared plus 4, du is 2x dx. I don't care about the 2. I need the x dx, and I've got it. So I can do a u sub here, and I have an arctan there. So I'm going to split this into two integrals. Factor out the -3. All right. Now for this guy, a squared is 4. So a is the square root of that, which is 2. And I get 2 times 1 over a arctan of x over a plus c, and a is 2. So sub that in. And then here, I'm going to let u equal x squared plus 4. du is 2x dx. So if I'm getting x dx by itself, if I want to get x dx by itself, I'll divide by 2. And I have that. So this is -3 times 1 over x dx is 1/2 du. So I'll put the 1/2 out front and the du to the right. And then this is u, but it's squared. So I've got u squared in the denominator. Now do not tell me that that's natural log of the absolute value of u squared. If that exponent is not a 1, it's a power rule. If it is a 1, it's a log. If it's a 2, got to do something else. So you're going to rewrite it and use the power rule. Now the 2's reduce over there, so I'm just going to bring that down. I'm going to bring the u up to the numerator. You want to add 1 to the exponent and then divide by the new exponent. And negative times negative is a positive. And that u is going to go in the denominator. And u is x squared plus 4. So you can leave it like that if you want to. You can distribute the 2 if you prefer. Either one is fine. But I claim, if I take the derivative of that and I simplify, I'm going to get that. And if I get a common denominator with that, I'm going to get that. So this is how we handle irreducible quadratic factors. After you've factored it, you write down the partial fraction decomposition, and every irreducible quadratic term, anytime you have an irreducible quadratic or an irreducible quadratic raised to some power, excuse me, I'm going to have a constant times x plus a constant in the numerator. Multiply by the LCD, and then this time, rather than choosing values of x that make factors equal to 0, you're going to set up a system of equations involving a, b, c, and d. And the way you do that is you distribute, collect like terms, get all the x cubed terms together, the x squared terms, all the x terms together, and the constant terms together. And then you say, okay, this polynomial is equal to this polynomial if and only if the coefficients on this side are equal to the coefficients on this side. So you set the coefficients equal to each other. You get these 4 equations and 4 unknowns. Solve for a, b, c, and d. I've got a, b, c, and d this time. Once you've solved, back substitute, simplify, and anti-differentiate using your basic rules. I guess we should write that down. Substitute, then simplify, and anti-differentiate. That's it. Yeah. I hope that helped, guys.